This session will illustrate the three different methods used to compute measures of dispersion and describe how these methods are used in practice. A consequence of these three methods is that there are right and wrong ways to compute limits for process behavior charts. These ways will be contrasted using several examples. Next, we cover some myths around process behavior charts and finish up with the four foundations for Shewhart's charts. This session will use the Understanding SPC text and the SPC workbook. We begin on page 24 of the workbook.
In this session, we will be talking about the three methods for estimating dispersion and the resulting correct and incorrect ways of computing limits for a process behavior chart. I'd like to begin on page 24 in the workbook, where we filled in this information earlier. We have the relationship between the various parameters. And here we find a standard deviation for X, and there we find a standard deviation for X, and down below we have two more standard deviations for X. Everywhere we look, there's a standard deviation for X. So if we estimate the standard deviation for X poorly, then the results will be skewed. So we need to talk about the different methods for estimating the standard deviation because they are not all equivalent. So turn please to page 28 in the workbook. It turns out there are three distinctly different methods for estimating the dispersion in a set of data. And these are outlined on page 28. If we have, say, K subgroups of size n, we can use these different methods. Method one, of course, is what you learn in your introductory class in statistics. So you put all the data into one big histogram, calculate a single dispersion statistic for this histogram, and use the single dispersion statistic to estimate the standard deviation parameter for the distribution of X. That's method one. Method two respects the subgrouping. We calculate a separate dispersion statistic for each subgroup. Then we average these K dispersion statistics and use the average dispersion statistic to form an estimate of the standard deviation for the distribution of X. So while method one ignores the subgroups, method two respects them. And method three, well, method three is indirect. We start off with the subgroup averages, and we draw a histogram down on the X-bar plane of the three subgroup averages. Find a single dispersion statistic using the K subgroup averages. Use this single dispersion statistic to form an estimate of the dispersion for the subgroup averages. If we measure the dispersion on the X-bar plane, then we're going to estimate the standard deviation for X-bar directly. And then we scale this estimate up using the formula in the middle of page 24 in reverse. We multiply by the square root of n to jump from the X-bar plane back up to the X-plane. So this is a two-part sneak up from below indirect method. Those are the three methods. Now we're going to illustrate these three methods using a couple of examples, starting on page 29. On page 29, we have data set 1, three subgroups of size 8. So we will use the three methods with this data set. We start with method 1, which puts all 24 data into one big pile and computes a single measure of dispersion. So the range for this histogram is 8 minus 2 is 6. The histogram contains 24 observations. So an estimate of the standard deviation parameter for the distribution of x is the range divided by its bias correction factor, D2. So that's 6 divided by the D2 for 24 data. You may find these bias correction factors on the inside front cover of your workbook. So there you'll find the D2 factor for 24 observations is 3.895. So 6 divided by 3.895 gives us a 1.543. Well, you say, I have a calculator that will do a standard deviation. Why don't I use that? Well, you can. You put all 24 data in the calculator, you push the magic button, and you get a S equals 1.551 based on 24 observations. So an unbiased estimate of the standard deviation parameter for the distribution of x will be S divided by its bias correction factor, C4. And the bias correction factor, C4, for 24 observations, again, inside front cover of the workbook, is 0.9892. 1.551 divided by 0.9892 is 1.568. So we've got a 1.55 and a 1.57. The original data are given the whole number. So these two estimates are pretty much tied, pretty much the same as each other. No practical difference here. Well, that's method 1. What happens with method 2? Well, we find the range for the first subgroup is 5. The range for the second subgroup is 5. The range for the third subgroup is 3. Their average is 4 1/3. Each of these ranges is based on 8 observations, and that tells us which bias correction factor we need to use. So our estimate for the standard deviation for the distribution of x would be R bar over D2. So that's 4 1/3 divided by the D2 for subgroup size 8, which is 2.847. That gives us a 1.522. Pretty much the same as up above. And if you want to use the standard deviation statistic, S for the red subgroup, 1.690. Put the 8 data in, that's what you get out. Put the 8 data for the yellow subgroup into your calculator, you get S equals 1.690 again. Put the 8 data for the blue subgroup into your calculator, push the magic button, you get a 1.195. The average of these 3 standard deviation statistics is 1.525. Each of these is based on 8 observations. So, an estimate of the standard deviation for x will be S bar divided by C4. That's 1.525, and the C4 bias correction factor for 8 observations from inside front cover, 0.9650, gives us a 1.580. Now we have just estimated one parameter 4 ways using 2 different statistics and 2 different methods. We have a 1.55, 1.57, 1.52, and a 1.58. All very cozy. Well, that's method 2. What about method 3? Method 3, we start off on the X-bar plane. We have 3 subgroups, so we have 3 subgroup averages, each one of which is based on 8 observations. So we have 3 averages, and the range of this histogram on the X-bar plane is 1. So the range of the averages is 1. So when we measure dispersion on the X-bar plane, we are going to be estimating the standard deviation for X bar directly. So An estimate for the standard deviation for the averages will be the range of the averages over D2. That's 1 over 1.693. 1.693 is the D2 for 3 data. You see, the range doesn't know if they're averages or what. It just sees 3 data points. So 1 over 1.693 is 0.5907. Now we go from the x-bar plane back up to the x-plane by multiplying using the formula in the middle of page 24 in reverse. We multiply by the square root of n. So an estimate of the standard deviation for the distribution of x would be the square root of 8 times our 0.5907, which is 1.671. Not as cozy as the first 4, but it's still in the same ballpark. And if we use our standard deviation statistic, well, we put the 5 and the 4 and the 5 in the fancy calculator and push the magic button. And the standard deviation statistic for the 3 subgroup averages is 0.5774 based on 3 averages. So an estimated standard deviation for the averages would be S of the averages divided by C4, 0.5774 divided by the C4 factor for 3 data, which is 0.8862, gives us a 0.6515. And to go from the x-bar plane back up to the x-plane, we multiply by root n. Each of the averages represents 8 data, so square root of 8 times 0.6515 gives us an estimated standard deviation for the distribution of x of 1.843. Now we have estimated one parameter 6 ways. We have 1.5, 1.6, 1.5, 1.6, 1.7, and 1.8, all reasonably similar. Just doesn't seem to make much difference, does it? Well, you've got to understand that data set 1 has a very special property. And that special property is shown on page 30. If we put data set 1 on an average and range chart, no points fall outside the limits. This data set 1, has no signals. It's pure noise. And in this case, well, what did we just demonstrate? Let's write it down. When the process is operated predictably, the 3 methods will yield similar values for the estimated standard deviation parameter. It just doesn't matter. They're all going to be about the same. However, what would happen if we had some signals? We're going to play a game here. It's sometimes an interesting thing to do. We're going to introduce known signals and see what those known signals do to our calculations. So we're going to subtract 2 from everything in subgroup 2. We're going to add 4 to everything in subgroup 3. So that's going to create signals on the average chart. Let's see what these signals on the average chart do to our calculations. And that will be data set 2 on page 31. Method 1 puts all 24 data in one big pile. And so the range for this histogram is 10. Again, that's based on 24 observations. So our estimated standard deviation for the distribution of x is the range divided by D2. That's 10 divided by 3.895, which is 2.567. Well, what if I use the standard deviation statistic? Let's find out. You put all 24 data in the calculator, push the magic button, you get a 3.274 as your standard deviation statistic based on 24 observations. So our unbiased estimate for the standard deviation parameter will be S divided by C4. That's 3.274 divided by 0.9892 gives me a 3.315, which is twice the size of the estimates we got on page 29. The first estimate went up about 70%. This one went up over 100%. So what did our signals on the average chart do to our method 1 estimates? Signals on average chart inflate method 1 estimates of the standard deviation parameter. All right, what about method 2? Let's see. Well, we take the first subgroup, the range is 5. The second subgroup, the range is 5. The third subgroup, the range is 3. Each of these ranges based on 8 data. So the average range is 4 1/3. So our estimate of the standard deviation parameter will be R bar over D2. So that's 4 1/3 divided by 2.847 is 1.522. Exactly what we got on page 29. If we use the standard deviation statistics, well, the standard deviation statistic for the red subgroup is 1.690. The standard deviation statistic for the yellow subgroup is 1.690. The standard deviation statistic for the blue subgroup is 1.195. The average of these is 1.525. And each of these is based on 8 observations. So our estimate of the standard deviation parameter is S bar divided by C4. That's 1.525 divided by 0.9650 gives us a 1.580, exactly what we found on page 29. So, what did our signals do to method 2? Average chart signals do not affect method 2 estimates, the standard deviation parameter. Average chart signals do not affect method 2 estimates of the standard deviation parameter. Well, what about method 3? Fasten your seatbelt. The subgroup averages are 5, 2, and 9. The range of these averages is 7. So our estimate of the standard deviation of the averages would be the range of the averages divided by D2. 7 divided by the D2 for 3 data is 1.693. Gives us a 4.135. To go from the x-bar plane back up to the x-plane, we multiply by the square root of 8 because each one of the averages here represents 8 original data. So our estimated standard deviation for x is the square root of 8 times 4.135 is 11.695. 7 times the value found on page 29. If we use S, well, S for the averages, put the 5 and the 2 and the 9 in your fancy calculator, push the magic button, 3.512 pops up based on 3 averages. So our estimate of the standard deviation for the averages would be the standard deviation of the averages divided by C4. That's 3.512 over 0.8862. 3.963. And once again, to go from the x-bar plane to the x, we multiply by the square root of 8. So our estimate of the standard deviation for x is the square root of 8 times 3.963, which gives us 11.209, 7 times the value found on page 29. So what did our signals do to method 3? Average chart signals severely inflate method 3 estimates of the standard deviation for x. Average chart signals severely inflate method 3 estimates of the standard deviation parameter. So now we have estimated the same parameter 6 ways, and we have a 2.6, a 3.3, a 1.5, a 1.6, an 11.7, and 11.2. People argue about whether to use the range or the standard deviation statistic, but that's not what matters. What matters is which method are you going to use. We didn't have to teach people all of this when people were doing it by hand because the easy method was the correct method. R bar over D2, real easy. But as soon as people had Pandora's box, little calculators that would give them the standard deviation, they wanted to shift from doing the range to doing the standard deviation. And they would unconsciously shift method at the same time. And it was the method shift that gets them in trouble, not the change from R to S. The difference is left to right, pale, in comparison with the differences top to bottom.
See, what are we trying to do here? We estimate the standard deviation so we can compute the limits, so we can filter out the noise, so we can detect any signals that are big enough to be of economic import. So our estimate of the standard deviation is basically how we filter out the noise. It's how we carry out the garbage. So we want to get rid of the routine variation and nothing but the routine variation. And what will let you do that? Method 2, method 2, or method 2?
So, from the beginning, there's a difference in these three methods and how they work. So on page 32, when it comes to separating potential signals from probable noise, method 2 is right. It has always been right, and it will always be right. World without end. Method 1 is wrong. It has always been wrong. Shewhart rejected method 1 in favor of method 2 on page 307 of his 1931 book. From the very beginning, it's been method 2 all the way, never method 1. And method 3, very wrong. I went into a plant in Indiana that had a piece of software that used method 3 to compute the limits. And they said, we never get a point outside the limits. Well, duh. But they continued to say, so, but our customer keeps telling us we're not that good. Surprise, surprise. There are right and wrong ways of computing limits. But if you don't know the difference in method 1, 2, and 3, you can get lost here. There's at least 50 ways to estimate dispersion. You can easily get lost doing all this stuff. So how do you tell the difference? Well, with method 1, how many measures of dispersion were computed before we estimated the standard deviation? There was one range, or there was one standard deviation. Down at the bottom of method 3, how many measures of dispersion did we compute before we estimated the standard deviation? One range, one standard deviation. But with method 2, how many measures of dispersion did we compute? 3 ranges, 3 standard deviations, a measure of dispersion for each subgroup, which is then summarized with an average, R bar, S bar, or sometimes we summarize it with a median. Multiple measures computed locally, summarized with an average or a median, is the hallmark of method 2. Now let's go back to page 28 and write a little bit on the margins of that page. These 3 methods have names. Method 1 is called the total or overall variation. It is descriptive. And as a descriptive statistic, that's why it's taught in your introductory classes. But method 1, the total or overall variation, makes an assumption that the data are globally homogeneous. Assumes global homogeneity for the data. Method 2 is the within subgroup variation. It is analytic. Whenever we're trying to separate the probable noise from the potential signals, we use method 2. Method 2's assumption is that the data assumes local homogeneity within the subgroups, that the subgroups are homogeneous internally. Method 3 is the between subgroup variation. It uses the subgroup averages and looks at how much they differ from each other, so it's between subgroup. And method 3 is generally comparative. We usually compute method 3 in order to compare it with method 2. Because what did we just learn? If there are signals in the data, method 3 is going to be inflated relative to method 2. Method 3 assumes global homogeneity for the subgroup averages. Now, which of these assumptions is going to be easiest to meet in practice? It's always going to be easier to achieve local homogeneity than it is to achieve global homogeneity. You see, this is the one assumption that the process behavior charts are built on. It has nothing to do with the shape of the histogram. It doesn't matter whether you use the range or the standard deviation statistic. It doesn't matter if you have a model or a p-value. What matters is that you have arranged and organized the data in such a way that the assumption of local homogeneity makes sense. And that's what we call rational sampling and rational subgrouping, which we will be talking about in session 7. Now, on the bottom of the inside front cover of the workbook, I give you some formulas, and throughout my books, I have a special notation for method 2. Method 2 estimators are indicated by reference with a word sigma written out with a parentheses. Some of these formulas are sigma of x might refer to r bar over d2, r tilde over d4, s bar over c4, s sub n bar over c2. Divide these estimates by the square root of n, and we have estimates for the sigma of x bar. Sigma of r might be d3 r bar over d2. That's a formula we worked out earlier on page 25 in the workbook. There's another formula like that, d3 r tilde over d4. I'm just going to ask you to take on faith. You work it out the same way as the one we did find. So when you see sigma parentheses x or sigma parentheses x bar in my books, you know I'm talking about method 2 as opposed to some other method. Now, I want you to just sit back and watch the slideshow. We're going to show you some examples. These examples come from a different textbook. And so we're just going to go through and look at the difference in method 1 versus method 2 with these 6 examples to kind of consolidate what we have been talking about. What descriptive statistics do. Descriptive statistics characterize the data. The average characterizes location, and the standard deviation statistic characterizes dispersion. So that nested intervals centered on the average with radii equal to some multiple of the standard deviation statistic, will bracket certain proportions of the data. Here we have the wire length data, the average 109, the standard deviation 2.8. So go 1, 2, 3 standard deviations either side of the average, and we find 69% of the data, 95% of the data, and 100% of the data, just like we expect. The beadboard number 7 data, we have an average of about 13, a standard deviation of about 3.5. Go 1, 2, 3 standard deviations either side of the average, we get 66%, 97%, and 100% of the data, pretty much what we would expect. Here we have the batch weight data. Average is 937. Standard deviation is 61.3. We go 1, 2, 3 standard deviations either side of the average, and we get 70%, 95%, and 99%. Camshaft bearing diameter data, 150 data. Average is 40, basically 50. Standard deviation is 2.8. We go 1, 2, 3 standard deviations. We get 79%, 91%, and 100% within the 3 different intervals. Hot metal delivery time data. And we saw yesterday the average is 60 minutes, the standard deviation is 30 minutes. And we go 1, 2, 3, we get 75%, 93%, 99%. And the creel yield data. Average is 34.92, standard deviation is 38.3. We go 1, 2, 3, we get 59%, 98%, 100%. So these 6 examples just illustrate the empirical rule. Descriptive statistics characterize the data. The average plus or minus 1 standard deviation statistic will bracket the bulk of your data. Here it goes from 59 to 79%. The average plus or minus 2 standard deviations will bracket at least 90% of the data. Here we went from 91% to 98%. And the average plus or minus 3 standard deviation statistics will bracket virtually all of the data. Here we went from 98.6 to 100%. Descriptive statistics summarize the data. They do not characterize the underlying process which produced the data. They assume the data are homogeneous, but they do not check to see if this is so. Some of our data sets are non-homogeneous. So at this point, we can say 3 standard deviation limits do not allow you to reliably separate homogeneous data sets from non-homogeneous data sets. Descriptive measures of dispersion do not differentiate between homogeneous data sets and non-homogeneous data sets because they are computed globally. If the data are not homogeneous, the global measure of dispersion will be inflated by the lack of homogeneity, but the localized measure of dispersion will not be inflated in the same way or to the same extent as the global measure. So to examine the data for possible evidence of non-homogeneity and to thereby characterize the underlying process, we must use localized measures of dispersion. So when the data have a time ordering, we arrange the data in time order. Find the differences between the successive values. These differences summarize the local short-term variation and are called moving ranges. We then summarize the moving ranges by computing the average moving range or the median moving range. When divided by the appropriate bias correction factor, these summary statistics provide a local measure of dispersion. So sigma of x might be the average moving range over 1.128, or it might be the median moving range over 0.954. So here's a simple example of 9 data, and the global method puts these 9 data into a histogram and computes a standard deviation statistic, 2.87. The local approach looks at the differences between successive values, gets an average moving range, 3.25, and converts that into an estimate by dividing by 1.128, and we get a 2.88. When the data are homogeneous, the global measure of dispersion and the local measure of dispersion will be quite similar. When the data are not homogeneous, the global measure of dispersion will be inflated relative to the local measure of dispersion. Now, in practice, we do not directly compare the local and global measures of dispersion. If we did, there might be less confusion on this subject. Instead, we use the local measure of dispersion to compute 3 sigma limits and look for points outside these limits. Notice 3 sigma is not the same as 3 standard deviations here. I'm using the words in a very precise way. So, for the wire links data, the standard deviation statistic was 2.82, and we had 100% within 3 standard deviations. And sigma is 2.85, and we have 100% within 3 sigma. So we'll say these data are homogeneous. Therefore, the underlying process is predictable. For the beadboard data, the standard deviation statistic was 3.46, and we had 100% within 3 standard deviations of the average. But sigma of x is only 2.14. So our 3 sigma limits have 11 out of the 200 points outside the limits. And if we look at this, you can see the process meandering around. These data are not homogeneous. Therefore, we judge the underlying process to be not operated predictably. The batch weight data. The standard deviation statistic was 61.3, and we had 99% within 3 standard deviations of the average. But sigma of x is 22.9. And so our 3 sigma limits have 56 out of 259 values outside the limits. These data are not homogeneous, so we judge the underlying process is not being operated predictably. Camshaft bearing diameters. We had 100% within our 3 standard deviation limits. The standard deviation was 2.78. But sigma of x is only 1.7. So we have 14 out of 150 values outside our 3 sigma limits. These data are not homogeneous, so we judge the underlying process to be operated unpredictably. Hot metal delivery times, we had 99% within our 3 standard deviation limits. The standard deviation was 29.7. But sigma of x is 20.96 or 21. So we have 7 of 141 values outside 3 sigma limits. And if we use the median instead of the average as our central line for the X chart, we would have 14 out of 141 values outside the 3 sigma limits. These data are not homogeneous, so we judge the underlying process is not being operated predictably. And then we come to the Creel yield data. The standard deviation statistic was 38.3. We had 100% within 3 standard deviations of the average. But sigma of X is 4.19. And we have 4 out of 64 points inside the limits. They just didn't get out of the way, so they got run over. These data are not homogeneous, and this process is not being operated predictably. Only 1 of our 6 data sets was homogeneous. 3 standard deviation limits bracketed all of the data for 3 of the 5 non-homogeneous data sets. 3 sigma limits detected all 5 of the non-homogeneous data sets. Percentage outside the 3 standard deviation limits range from 1.4 to 0. Percentage outside the 3 sigma limits ranged from 94% to 0. The only reliable way to check for homogeneity is to use a localized measure of dispersion. Method 2, method 2, or method 2. If it ain't method 2, it ain't right when it comes to filtering out the noise.
Now we return to the Understanding SPC text to consider the myths and foundations of process behavior charts. This material begins on page 76.
Because of the 2 schools of thought about SPC, the one started by Pearson and the one started by Schuhart, several myths have grown up about process behavior charts, and they seem to have a life of their own. So the first of these myths, it has been said data should be normally distributed before they are placed upon a process behavior chart. I hope I've dispelled that myth already for you. Schuhart wrote in his second book, "We are not concerned with the functional form of the universe," that is the probability model, but merely with the assumption that a universe exists. And the original is in italics. The italics are Schuhart's. The picture on the next page comes right out of Schuhart's first book. It is not a bell-shaped curve. It's skewed. And yet it's at least reasonably predictable, Schuhart says. Reasonably in control. Myth number 2. It has been said the process behavior chart works because of the central limit theorem. Now, the central limit theorem is a true theorem. It's published by Laplace in 1810. And it goes something like this. No matter what the shape of the histogram for X, the histogram for X bar will look more and more like a bell-shaped curve as the subgroup size increases. So while the original distribution are totally different, by the time you get down to subgroup size 10, you can hardly see any difference in the histograms for X bar. So you show a statistician an average, and like Pavlov's dogs, he begins to drool because he knows he's got normality. That makes so much sense what we do simpler. So the central limit theorem lies behind many of the things we do. The central limit theorem is what makes the t-test robust to non-normality, for example. But there is no central limit theorem, at least no strong central limit theorem, for measures of dispersion. So the histogram for the ranges do not converge in shape as n goes up. In fact, they diverge in shape. They have the greatest similarity when n equals to 2. When we have already bracketed approximately 99 to 100% of the values by brute force, we do not need to appeal to any theoretical arguments to understand that a point outside the limits is likely to represent a signal. The conservative nature of 3 sigma limits make the central limit theorem irrelevant. This was illustrated back there on page 64 yesterday. Undoubtedly, myth number 2 has been one of the greatest barriers to the effective use of process behavior charts with management data and process industry data. Whenever data are obtained one value per time period, it will be logical to use subgroups of size 1. However, if you believe myth number 2, you're going to feel compelled to average something in order to invoke the blessing of the central limit theorem, and the rationality of your data analysis will be sacrificed to superstition. Central limit theorem is true, but it's not the foundation for the chart. And Shewhart, with his usual thoroughness, took about 40 pages to examine that idea and say, well, we can't really use this because it doesn't really work for measures of dispersion. Myth 3. It has been said observations must be independent. Data with autocorrelation are inappropriate for control charts. Zoom in here. There's a footnote down here at the bottom of page 80. A large positive autocorrelation will exist when the data display 2 characteristics. Successive individual values are generally quite similar, while 2 non-sequential individual values may be quite dissimilar. In other words, you've got to have both properties to have a large positive autocorrelation. What that means is that if you have a large positive autocorrelation, your process is moving around. If your process is moving around, it's unpredictable. Here's an example out of Shewhart. It had a correlation of 55%, which is detectably greater than 0. And the chart is on the next page, page 81. And Shewhart wrote, there's a quote right below this, Shewhart wrote, "We have points outside the limits. That's evidence we have assignable causes. We started looking, we found the assignable causes, we fixed them. We collected more data and got the second chart. The second chart says you don't have any assignable causes. So I told the guys in research they were wasting their time. They kept looking anyway. They couldn't find anything to fix. Here then is a typical case where the process behavior chart tells you when to look for assignable causes and when to stop looking and let the variation be left to what you are called chance." You see, the purpose of analysis is insight rather than numbers. The process behavior chart is not concerned with probability models, but with using data for making decisions in the real world, when to look and when not to look for assignable causes. Process behavior charts have worked with autocorrelated data for over 80 years. So if somebody says, you can't use autocorrelated data on a chart, they don't know what they're talking about, number one. But just tell them Shewhart did, figure out where he went wrong, then I'll talk to you. And myth number 4, it has been said the data must be in control before they can be plot them on a process behavior chart. I found this statement in a paper I was refereeing. It had been written by a professor of statistics at a state university. He ought to have known better, but he didn't. Why would you say something like this? Because you say something like this when you think when you're using method 1 to compute the limits.
Dr. Wheeler, I get challenged on all 4 of those myths weekly, so.
Yeah, I'm not making this stuff up. And you see, it comes right out of the statistical view. If you're thinking in the statistical approach, you got to have a probability model, and you got to have a fixed p value, and yada yada yada. All of that comes up.
If I can summarize myth number 2.
Oh, there's several of them, but go ahead.
Just to clarify in my mind's eye, what you're saying is that the individual moving range chart is not sensitive to false signals when the data is non-normal. Is that a correct interpretation? Because that's different than what I thought was true.
Yes, because the reason it's not sensitive to false alarms when the data are non-normal is 3 sigma limits are so conservative that it just doesn't matter. Page 64 is a very important page. That's not normal. That's not normal. That's not normal. 3 sigma limits. I mean, when you have really skewed data, you've got a barrier here, a barrier here, a barrier here. You don't get data like this without a barrier. And so the one limit becomes absurd, but the other limit continues to protect you on the elongated tail.
Thank you.
Very important picture, page 64. And that's one of the antidotes to that way of thinking. And once you've done this, then you don't need to appeal to the central limit theorem. That means you don't have to average something to invoke the central limit theorem. And so myth number 2 has been one of the greatest barriers to the use of the XMR chart. The XMR chart, as I told you, was invented in 41-42 by W.J. Jennett. And if I go through all the textbooks I can find, I can get 17 pages and about a dozen examples on that technique in all the textbooks up until 1980s. So when I wrote Understanding Variation, which was the first textbook devoted entirely to the XMR chart, and with 32 examples, I completely overwhelmed all that had ever been written about the XMR chart before then. I was talking to Dr. Deming one night in 1985, and he said, "Tell me about this XMR chart, Don." He'd seen one at a client that we were both working at, and he had never done one. You have 2 pages in this textbook and 2 pages in that textbook and a page and a half in this textbook. It was a technique that was really out on the margin and nobody had paid much attention to it. But I started working in industries where it was a process industry. The guy said, "Look, I get 1 rail car a month. I don't want to wait 3 months. I get 1 number per rail car. I don't want to wait 3 months to plot a point on my chart. Periodically collected data, duh. You need subgroup size 1." And you go back and read Schuart, and he says, "It would be nice to have a way to do subgroup size 1, but I don't see how to do it." That had to wait until the 40s before we figured out how to do that.
So following with that thought, there's no real value into using a moving average, moving range chart
No,
for non-normally distributed data. That's correct? That's true?
correct. Foundations, page 82. Foundation 1, I hope you understand now, 3 sigma limits work by brute force. They are sufficient to cover everything you need. They'll give you a p-value close to 1, regardless of the probability shape of your histogram. Foundation 2, we're going to use the within subgroup variation, method 2, as the way to compute the limits. Foundation 3 is what we want to talk about this afternoon. The conceptual foundation of Shewhart's charts is the notion of rational sampling and rational subgrouping. And foundation number 4, Shewhart's charts are effective only to the extent that the organization can use in an effective manner the knowledge gained from the charts. This is where you put Deming's 14 points. He's talking about obstacles to organizations behaving rationally. And if you want to dig more deeply into that, I recommend Henry Neve's course, which you can download free from our website, 12 Days to Deming.